Okay, so what we did. There are two projects we put a lot of time into. FISM and CEA. FISM, F-I-S-M, Fault Inclusive State Machine it was kind of a dead end. We did trial and error. This was a try. It errored. It kind of solves the wrong problem. It tells what to do once you found an error, but not how to find the error, and we're supposed to be finding errors. So it didn't really pan out. Read it if you've got the time, but you can probably skip it. CEA, changing element algorithm. I really loved CEA because I am biased and that I had the basic idea and hashed it before hashing it out with my teammates. Wong didn't really seem to like it. I'm still not sure why. Anyway, so I'm going to talk about CEA because I still feel that this is the best starting point to integrating the machines, the whole point of this project. So, what we tried to do is we want to look at the state machine and figure out if anything the state machine does when working will accidentally set off the fault tree's top level event. If just natural processes can result in something bad, that's an inconsistency and we want to automatically detect it. So that leaves the problem of taking a state machine. How do you know when it will set off an error? And for this we went to the fault trees and using a bit of logic came up with a few logical facts about it. Imagine a fault tree that, for the simple example, I'll get complicated later, for a simple example, imagine that there are no knots in it. It's just ands and ors. Okay. And occasionally I can change one of the basic events from true or to false. I cannot cause a top-level error by turning a basic event from true to false. You can work this out for yourself looking at ANDs and OR gates. If I turn a node from false to true, there is a chance, not a guarantee, but a chance it's going to set off a trigger that leads up to a top-level event. So, keeping that in mind, the only places in the state machine that run a risk of causing a top-level error are the places that change a basic event from false to true. Now, as I mentioned, that's only without knots. If you do have a knots, it's actually a lot easier than you might expect. Basically, look at the basic event, look at the top-level event, count the number of NOT gates in between those two things. The short conclusion that we worked out for this, if there's an even number of NOT gates in between them, then it's still true. It can only cause an error by switching from false to true. If there's an odd number of NOT gates in between the basic event and the top-level event, it's actually reversed. You can only trigger it by going from true to false, can never trigger it going from false to true. Which sounds like a crazy claim. I think part of the reason Wong didn't like this is we didn't come up with a formal proof for this. It was just kind of a logical, we know X, Y, Z, that proves A, B, C. I don't know. I can't, for the life of me, think of any example where this doesn't pan out. And I spent quite a bit of time on it, but moving on, stop complaining, let's keep going. So, in our state machine, and for the rest of the examples, I'm just going to say false to true. It can work the other way, but it's easier for me to talk about it if I just say it that way. So, over here, basically we're looking for anything that will turn a basic event from false to true. That's the purpose of this. We want to figure out whenever this changes a basic event to true, that's where a risk has a chance of occurring. So, that is our first step. Let me save